guys, so now we're up to the plum pudding model, right? So I'm gonna draw a model of that, okay? And we agreed that J.J. Thomson said that it's a mass, okay, of positive charge, right? In which negative electrons are embedded, okay? So we're gonna do that there. So recap, okay, no problem. All right, so it's called the plum pudding model, and that's Thomson. Okay, all right, put it right there, Thomson. Okay, so along comes Rutherford, right? And he does another famous classic experiment, guys. Okay, so we gotta know this. Now the thing is, don't just memorize it for memorizing's sake. Understand the parts of the experiment, understand, the observations, and understand the results, right? Okay, don't just guess and memorize the stuff, because you won't be able to commit it to memory, all right? Just it'll go in one ear or the other. So Rutherford, right, did a famous experiment called the gold foil experiment. Okay, the gold foil experiment. Well, what did he do? He simply had a radioactive source, right? Okay. And inside that radioactive source, he shot something called alpha particles out. Now he was testing with different, different metals, different foils, right? So he's shooting alpha particles at, okay, an actual gold foil. So, all right, gold foil right here. All right, bam. Now he also had a screen here, okay, with a special chemical on it, right, that allowed him to see when and where the alpha particle struck after it was shot at the gold foil. So this thin dotted line right here, that's my gold foil, okay? Now the thing you have to appreciate, guys, is that the alpha particles, right, their symbol for alpha, if you look on table O, right here, table O, you will see that it's represented by 4,2He, all right? And it looks like helium, right? Now, they're special in the fact that they're coming out of the nucleus, okay? Plus, they have no electrons. So alpha particles have no electrons. And we agreed if you have the same number of protons, same number of electrons, and you remove the electrons, there's no electrons, that substance will have a positive charge. So make a note, alpha particles are positively charged, okay, particles, okay, being shot out at the gold foil. Now, what he observed mostly, right, was that the majority of the alpha particles just zoomed, bam, just passed right through. So I'm gonna draw a bold line representing that the majority of the alpha particles just passed right through, okay, and they hit the screen back here, no problem, okay. Now, analogy we have to give also is that to put context to it, is that the alpha particles compared to the gold foil, right? Alpha particles are like a massive artillery shell, like a shell from a tank or something. And the gold foil, you can think of it as loose leaf paper. So that's the analogy. And you think that if you shoot like a large, bullet or a large artillery shell at loose leaf paper, it will just tear it up and go right through, right? But what also he observed, guys, okay, now he didn't observe it a lot, but he still did observe it, was that there were deflections, right? Okay, like that. And there was also even where the alpha particles bounced back, okay, towards him, all right? So think of a large huge bullet being shot at loose leaf paper, and the bullet coming back towards you. Okay, so that's the context. Okay, so that was pretty incredible. So let's go with the observations. Observations of this gold foil experiment. Firstly, most of the alpha particles passed through the foil. Okay, most of the alpha particles pass through the foil. So what did that prove? That proved that the atom So this conclusion. You concluded from that, all right, concluded that the atom is mostly empty space. Okay? So we don't guess, because they can ask you, how did they prove that the atom is mostly empty space? Or they can ask you, what did the alpha particles mostly passing through the foil prove? Okay, so there's no understand observation versus the conclusion. Okay, no problem. All right. Now, also, guys, also another observation was that you saw deflections and even strong repulsion, right? Now, the deflections and the repulsion were not that many, but they still existed, okay? I think the ratio is 1 in 20,000, okay, in terms of the amount that passes through to the amount of deflections and repulsions you saw. But you don't have to worry about that. The main thing is that it did happen. You saw the deflections, you saw the repulsion, right? So, from this, especially the repulsion, right? And, you know, he concluded that we know that light charges repel, right? So he concluded that there was a positive, right? Small, dense core, all right? So now we're moving from the Plum pudding model to where now we have a positive, small, dense core. How do you conclude it's positive, okay? Because light charges repel. The alpha particles are positive in nature, and they're being repelled by something in that small, dense area. So you also can conclude that that small, dense area has something positive inside of it, okay? Now, this small, positive, small, dense core is called the nucleus, all right? Bam. Okay, so the nucleus is always positive because we know now the nucleus contains protons, right? So Rutherford's model now is going to look like this. We have our nucleus, all right, our tiny nucleus. We draw a little bigger, like that, okay? And around it, all right, we have the electrons traveling freely, okay? No problem. So we'll move on to the next model in a second.